We're on episode 16 of the MiSTer Dev Core Journey. This time we'll learn all about the MiSTer framework, how it holds all the core together. I'll talk through each part and then we'll give the working game a run through. So this episode we're going to wrap up the core we've created, putting it into the MiSTer framework. That's going to allow us to have control inputs and also take advantage of features like HDMI output, screen rotation and all the video options like scanline effects that are part of the MiSTer environment. Here's the topics we'll discuss in this episode. Looking at the developer website to understand where to start with the framework and how to use it as a reference. I'll describe the overview of the framework and how all the parts fit together to make the final core. How to go about porting your core code into the framework. We'll take a look at the main game file in the framework that glues it all together and take a deep dive on the individual modules that need to be included. We'll look at MRA files and the way you need to structure them to get the main ROM files that are separate from the main core to load ROM information into the core on startup. We'll see about the specific arcade video module that can be used to provide flexible video output, including screen rotation. On-screen display menu settings will be covered and how they are linked to the control scheme or the dip switch settings of an arcade game. Finally, we'll have a brief discussion on some items not implemented in this version of the core. On the way out, we'll have a little play of the game to see if it was all worth it. If you go to the MiSTer development GitHub mkdocs MiSTer, this site gives all the info you need for setting up your MiSTer. We're mostly interested in, however, the developer reference section, and here it's just a written instruction of what I'll be covering in this module. I want to give an important clarification at this point. It's probably clear to everyone following along in this video series that I'm not a high-level FPGA developer. I'm not even a programmer by trade. I'm simply someone with a passion for the hobby that really wants to get some cores working on the MiSTer. You've probably seen me struggle along, or maybe you haven't seen me struggle too much because I haven't shown those parts in the videos. I can honestly say though that the struggle to do the framework part has almost been worse than the rest of it. I think there's a few reasons for that. One is that it's the first time that I've had to get intimate with the code from the FPGA superbrain gods. If you take a look at the files that we'll get into, you can see some really amazing code and associated functions. It's almost like looking into the matrix itself. However, with that comes the fact that these guys have no idea how stupid someone like me can be, and how I need immense explanation to get things working. That leads me into the second point. While there is a cursory explanation about this MiSTer framework on the site I've pointed to, this stuff is far more complicated than that document alludes to, and in reality it needs a far deeper explanation than what it's doing. In addition, these interweaved sections of code around the sys folder, out of plain sight, often are not declaring or defining variables that are essential to the core to compile correctly in Quartus. But maybe one day there can be some documentation to improve on this, or the likes of myself can piece together like a 10,000 piece jigsaw puzzle and pass on this Rosetta Stone of information to future generations. Or just do what I did and ask the folks over at Discord to tell them what on earth is going on. A special shout out to Wickerwacker, Birdie Bro and Jimmy Stones for help over there getting me to the finish line, or at least the intermediate sprint line on this core. So on this site we've got various different sections. Porting cores just tells us, basically talking about starting with the Spectrum core and some important features. We're going to see some of these. Core string configuration. So this is where we set up an interface between the controls. Dip switches can be set up in here, and a few other items. Essentially it's everything that's on the on-screen display. We've got the explanation of the top level of the core, so some necessary parts to understand like joystick I/O buttons, scan doubler, etc. There's an explanation of some core names. We're doing an arcade game, so it's pretty set what we have there. We've got a look at MRA set names. Again, this is to do with what you'd call your MRA. We've got the MRA format, which we're going to step through in a minute. It basically sets what you put in your MRA file. It helps you load your ROM file from your main ROM into your core. And then there's just some other useful links and other documents you can look at. So we'll come back to this sporadically just to have a look at some best practice items for doing some of our files. For the MiSTer framework, we have this general setup as shown in the diagram. We start with the EMU module in the center. That's the core specific file that is the root directory of our core. That file connects the core specific information of the actual game on this side to the entire library of the functions that sit on this side. The EMU points to systtop, which connects all the modules in the sys folder, which connects either actual I/O pins on the FPGA or eventually to Linux libraries that are being used for interfacing. When developing a core, we need to be cognizant of four entities: the Arcade-Game.sv file, the game-specific module, the connection to the OSD and the ROM file through what's known as the HPS bus or the status bus, and then finally the clock PLL that ensures the system clock is set up and may also be driving a video clock or the actual game clock. The items inside this orange box will all need modification when porting or creating a core from scratch. The items outside the box are all the MiSTer framework files that don't need to be modified in any way, which is good news because they are horribly complex. So I'm in the Arcade Tank Battalion area of the GitHub now, and we're going to have a look at the folder structure. So in the folder structure we've got the base, and we've got these files here, so Tank Battalion QPF, QSF file, QWS and SV file, and then we've got the files quip here. We'll get into what these do, but we've also got a RTL folder. The RTL folder is our game core, so it's all the files we've written up to this point. There is an additional PLL, so this is the system PLL that comes with all cores that we're going to port, and we use this to include our own clock core. So you remember maybe that our clock core was 18 megahertz. We're just going to include an 18 megahertz clock into this PLL that already exists. So the rest is pretty much the same. One thing just to note is a bit of an oddity. When I was porting across, TLL chips had a space in the title, and when trying to pull that into the MiSTer framework, it didn't like it at all. Had to have an underscore there. So no change really other than that, just the underscore. Then we've got the sys folder, and as we said, the sys folder holds all of the system files which we do not modify. We just pull across that sys folder, and this has got all the functions effectively of the MiSTer in there, and we reference it just in that SV file. This one here, Arcade Tank Battalion SV. That's where we're setting it all up. But if you remember in the diagram I just showed you, the actual top file is in this one. It's systop.v. So that's the top module, but we never actually need to touch that one. We're only ever touching this SV file here. So the first thing to do is, if you're pulling across a core, I've pulled this from a core called Dotori-kun, and it's a very simple game that is a little bit like Head-On, if anybody knows that game, Head-On. But it was an interesting core to pull across and just have a look and modify it, because it's really simple. So the first thing to do is you pull that file, that whole folder with the RTL sys and all these files into where you want it, and we start renaming all of the files here. This was Arcade Dotori-kun. We've changed it to Tank Battalion, Tank Battalion, Tank Battalion, Tank Battalion. And then if we go into each individual file, so this file here, the QPF, we just need to change the file name to Arcade Tank Battalion there, and that's it. And then we can come out of it. We save. Change the name again of that one. Now here, the only thing we want to do here is we need to remember, if you've got a game that requires rotation, so let's say you've got a game that's a vertical game like we have, it's going to use the frame buffer, the DDR, the DD-RAM as the frame buffer to rotate the screen. So we need to make sure that set global assignments MiSTer FB equals 1, and so we take away this hash. That's got to be done. If that is not done, it will not be able to rotate the game. Okay, so that's important to make that change. This QWS file, nothing much interesting in there, so we just rename it just for fun. And then we get into the main Tank Battalion SV, which is the main one to change. We have a files.quip. This is really important that we put all of the file names that are in that RTL folder. So we include all of those. We don't need to include the PLL file because that's already included in one of the other quip files. But we do need to include the Arcade Tank Battalion SV file as well. So what happens when you open Quartus is it looks in this file and it includes all of these files that are written in here. Alright, let's have a look at the Arcade Tank Battalion SV file. So here the main structure is, it's this module emu at the top, and this is defining all of the in-out parts of the MiSTer. So we've got the clock, reset coming through, the HPS bus, so that's input-output module, video, and then things like HDMI, VGA. This is that frame buffer we were talking about. So yes, it says here, if you need a frame buffer in the DD-RAM, make sure that FB equals 1 in the QSF. And if you don't do that, you'll get an error message saying this doesn't exist. That was a head scratcher for me for a long time. I wasn't on compile, this was saying this doesn't exist. So I suddenly realized that hadn't been changed in the QSF file. So none of this stuff needs to be changed. We can basically just ignore it. When we come down to here, default values, we need to grey out this if we are assigning anything to the DD-RAM, obviously we just said we're going to use it for the frame buffer, or the system is. We need to make sure we're not doing anything with it. So comment that out, otherwise you will have an error saying it's being assigned twice. So everything stays the same until this point. And from this point we've got our definition of what they call the conf string, and this is effectively what appears on the OSD, the on-screen display, for us to change settings in there. But it's also important because it's going to define the controls. So down here we have the controls defined. We've got the aspect ratio defined that we can change, and here I've also defined the dip switches. So I'll come back to this in a minute, exactly what all this is doing. This is important here too. This is also defining the aspect ratio. I'll come back to this as well. After that, definition of clocks. So this is linked to the PLL. As I said before, there's always a PLL associated with this module. It will take in the 50 megahertz reference clock always, and we'll have different clocks coming out depending on what you want to do with your core. So we've got a video clock, and then we've also got my core clock, which is 18 megahertz. We pass that through. We've then got a standard definition for HPS, which is setting up things like buttons, scan doubler. This is the status buffer, which is very important. All the stuff we'll be looking at is referenced on this status buffer. Here is an entity which is the part that downloads the ROM from the MRA file into our core. So that's what what these variables are, and we'll look at that when we look at the MRA. We've got our joystick interface here, and that's what we reference for our controls. Then we've got our HPS I/O, and this is always the same. We don't change this, but this is effectively just linking all those bits you saw to the HPS I/O, which I guess eventually goes back to Linux input output. But again, we don't need to change this part. These are where we set up the control. So this is individual to each core. We effectively take the joystick that we had up here, so that's a generic joystick output coming out, but then we make it specific to which buttons that's going to mean in our core. So I'll pass that to our core in a little bit. Here is definition of the dip switches on our game. So very similar to controls if you want. We're looking at the OSD part that we looked at earlier, and we're then setting up variables, and we can pass that to our game. Again, I'll step through that when we look at the MRA. For clarity, I've just described what each dip switch setting is. We've got a clock divider, which just sets a pixel clock based on the video clock. And then we've got our video section. So the important thing to note on this one is before I was passing out an RGB signal out of my core with an H blank and a V blank and a composite sync. If you remember, that's how it showed up on my screen. Or the VGA version, I was passing out each one separately. The arcade core actually wants it to be a bit different. So it wants you to pass out the RGB individual signals. It wants you to pass out H blank, V blank, H sync and V sync, and then that gets fed into this thing called Arcade Video, the module, and we specify as input entities how many bits are going to be used in that. So that's how many color depth bits. We're going to have red, green and blue 333, so 3 bits deep for each of the colors. That makes 9. And then 260 is the horizontal resolution of the game. And I've played around with that a little bit, and it doesn't affect it too much. I haven't been able to change it too much. I think the Arcade Video module is quite clever in recognizing what it's receiving, but I think that is a sensible input there. So that's necessary for Arcade Video. If you have a game like our game where you need to rotate it, we need this line here, which is called Screen Rotate. That's a module within this Arcade Video .v in the sys folder, which allows us to rotate the video. And we've got some video options here, which is, do we rotate it yes or no based on a status bit? Which direction do we rotate it? So you can rotate it clockwise or anti-clockwise. And then this wire flip, this is if the core can actually flip on a hardware level, like Centipede I think can, flip it vertical either way, depending on if you've got a sit-down cocktail cabinet. After that, to end up, we've got our game part of the module, and it's just the input to our game. So as I said before, we've got RGB separately, hsync, vsync, hblank, and vblank. It needs a reset input, as we've seen lots of times before. We've got our clock, which is the 18 megahertz clock going in, and that's what is then set up in terms of all of our dividers to get our sync signals and everything, as you've seen throughout all of the journey. We've got our controls defined, so that is the joystick up, down, left, right, shoot. We've got start buttons, coin buttons, test toggles. We've got our dip switch settings, which will change some things in the game. And then here is a new addition, and we're passing this information here to be able to download the ROM from the MAME zip file into our ROM at game startup. So MiSTer takes control, passes the data through, and we're actually loading the ROM with the information it needs on startup. Whereas before we hard coded the actual data into the ROM. We can't do that if we're releasing it, obviously, because it will hold that proprietary information, which is not legal. So this is the way that they pass that data through into the ROM file, and we'll have a little bit of a look at how we do that. Okay, so let's have a deeper dive look at the this conf string. So this is all related to setting up the core and linking it to the I/O, the OSD menu. But the first thing to look at here is the aspect ratio. And if we go back to our original part here, we go to the core configuration string section. And effectively what it's telling us here is it's giving us instructions of how we need to set all of these different entities up. So if we pull up the example, we've got a tank battalion, so that's just setting out the name. So that's always the same, we're always going to have A and then the name of the core. After that we've got this H index, which is says it's a prefix, which hides the option if menu mask is set. So we don't need to worry too much about that. We're more worried about what comes afterwards. So O, index 1, index 2. So that's an option and allows us to select between different options in that menu. And so what that's doing is, so if we say we forget the H0 and we just go from O, J, K, that's saying the aspect ratio can be an optional choice between original or full screen, and that is put into the area variable JK. And what that actually means, that JK is equivalent to the status with bits 20 and 19. Now I think in later versions you can actually put O square brackets 2019 to be clearer. That is equivalent, the JK, to the status bit 2019. So all of these things we're going to put here are going to have equivalent locations in the status matrix, effectively, or the status variable. We just need to know where to find them. So that aspect ratio 1, JK, is 2019. And that'll be able to change between full screen or original width. Then we've got orientation, vertical or horizontal. That is, again, it's another O, it's option, and it's in bit location 2. Then we've got whether the scan doubler effect is on, and that's going to be an option, and it's going to be in bit 3 to 5. It's not 35, it's going to be 325. So it needs quite a few bits there to get all those options. Now the next one is my dip switch settings. So I have put as option, we have a test mode on or off. That's in bit 8. We've got then lives. There's an option between 3 or 2 lives. That's in bit 9. And then we've got a bonus. We need 2 bits to define those 4 options. And that's in bit AB. And then how many credits you get per coin is in CD. And then whether it's a cabinet or cocktail or upright cabinet, it actually makes no difference in this game. That's in bit E. So those are all, actually, if we look further down, the dip switch settings, those all equal status 8, 9, 11, 10, 13, 12, and 14. So they're not letters. They're defined as letters here, but they're actually numbers in the status. As I say, I think you can change that in the latest version if you want. We then go down to the reset. The reset is always R0. So that's status 0 in the status bit 0. And that allows us to, if we press the reset button on the MiSTer, the whole system resets. I think it's linked to the Linux side that drives that. Everything gets halted and rebooted. Then we've got the joystick options. So this J1 is your specific options for your game. So when you want to define new controls, this is what the menu asks you to do. So it says what shoot, what start, and it goes through this list, and it's setting up in the status variable there. Now you also have this one JN, which is like your defaults compared to a Nintendo controller, and I've just grayed this out because I don't want this to be applicable. With me just starting out doing these cores, I wanted to just make it a bit simpler. We've then always got this V build date at the end here. That's standard. So this is pretty simple compared to some. You can add lots and lots of different options on there, obviously depending on how complex your core gets. Alright, so in clocks, what we need to make sure of is if you bring in a core that you're going to modify, there's going to be a PLL in the in quarters that's associated with this. It's called PLL, and you need to go in, edit that PLL, and make sure that your clocks, in terms of your outclock 0, 1, 2, or however many you've got, are going to line up. So in my case, I had to add this clock 18 that feeds the game. So other than that, pretty simple. No change for any of these items down here. And then, as I said here, this is where we define the joysticks, and then also the dip switch settings. So this is linked to that menu that we just saw. So again, whether it's rotated or not is status bit 2. As you can see, it's always to do with this status bit, so it's pretty useful in terms of understanding. Then in terms of FX, that's the scan doubler we saw before. We've got bit 3 to bit 5 is where the scan doubler is. So now when we get to the game, got this little bit of code here, and so the reset that goes into my game is a definition of the system reset, or if the status 0, which is also reset state, or you're pressing button 1, which is the reset button on the MiSTer, or we're in the state called ROM download. Now ROM download is the input-output control download and the index, whether the index is 0. If the index is 0, it means it's downloading the ROM. So effectively what's happening is our game isn't allowed to work until there's no reset buttons pressed, or the download button, the download has happened, and that download is the ROM data going into our ROM file. So to understand a bit more about this download stuff, I think the first thing to do is have a little look at the MRA file. So if I go into release, I have the Tank Battalion MRA here. So what have we got? We've got, it opens up just with the same thing, saying it's the description. We can add a lot of fields in here depending on what we're actually doing. For this particular core, it's pretty simple. So we've just got name tank battalion. We've got the main version, which can vary. I'm not sure how sensitive this is. We've got the set name, which is tank bat. That's the particular name of what it's called in MAME. We've then got a timestamp just for when this MRA was written, a year for when the game was, and the manufacturer, Namco, and then what kind of game it is. It's a maze game. We've then got the associated RBF file, which is very important, tank battalion. So when we open up the MRA file, it's going to make us look for the associated RBF file. So that's got to be, you know, the right name. And then the most important thing is this ROM index. This is picking up the ROM from MAME, and this has all got to be correct. So the zip name is tankbat. I didn't include the MD5. I can do, but I didn't want to make sure it was triggering something wrong. And in that file, we've got 1, 2, 3, 4, 5, 6 files, which are, if you remember, we've got 4 program ROMs. This is the tile graphics ROM, and then this is the color PROM. Now they don't always have the color PROM in the ROM file in MAME, and if they don't do that, what you can do is you can add the individual hex values as a separate part here in an MRA. If you look in the Pac-Man core, they add the PROM file in there, so because it's not actually in the individual game, I don't believe. So what this does is effectively puts this in a big variable, in a big array, set of memory, if you will, one after the other, and it just transfers from the memory that's created here, loading them all up one after the other, into the ROM that you specify, depending on how you specify it. So in our case, we've got a that's 2K, 2, 4, 6, 8, 10K there, and then that's 256 bytes. So 10 and 256. So we need to obviously have around, let's say, 12K's worth of file to transfer this data from here into the ROM files, and that's what we're going to see. So if we go down here, our input-output address is 13 down to 0. Now the reason why that is because the size of the data was actually 11 down to 0, and we're actually using a couple more bits just to choose the data. We'll see that in a minute. So now if we go into the actual game file, we can see what it's doing in terms of loading this data into the ROM. Go into RTL, tank BFPGA. So what have I changed in this top module? I've put in a hsync, vsync, hblank, vblank. The only change on here was I had to define what the hsync was. Now I've put the hsync to be, or the hblank, sorry, to be H256 star. Now I had always thought that the hblank was H256, but actually someone watching the earlier videos had preempted this, and he had said that it wasn't working for him. It was always offset by a full character, 8x8 pixel character. It was off. And the answer to that was trying the H256 star, and that works out just fine. So that's what we defined as hblank. So we've passed those back, and we're also passing back the individual red, green and blue, but we're also now getting the controls, the dip switch, and these the ROM download, 13 down to 0 for the address, 8 bits wide, and then this write enable pin to tell us when it's wanting to do it and when it's finished. So no other big changes there. So if we go down to our first one, I think it's a prom file. No, we're actually doing the character ROM first. So what we've had to do is we've created a dual port ROM file. So we've seen before we had a dual port RAM for our video RAM. So why did we do that? We had it so that the video circuitry could look at the video RAM and the CPU could write into the video RAM. So we're doing the same thing here with all of our ROM files, and we're making it dual port to be able to have the CPU constantly reading the ROM when the game starts, but prior to the game starting we want the system to be able to write into the ROM with the data from the MRA file. So we need to change all the ROMs to dual port ROMs. That's not a big change. All it needs is everything doubled up. And now we've got a write enable. So basically the ROMs are effectively just RAM files because they've all got write enables. We just choose on the ROM side, which is side A, not to invoke the write enable. So it's always 0. On the load side, which is side B, we do load it if the download is happening and it's the right ROM that we're writing to. And I'll get to how that's defined in a minute. We also have clocks, which are system clocks here. Now it's important to remember, one thing I didn't realize, but it's absolutely paramount to remember, is that when we're downloading this data at the beginning from our MRA file, the system clock that we're using in our top module has to be the same as the clock with which we're writing the data into this ROM file. If we don't do that, it's not going to be happy. In our case, the system clock is 18 megahertz and the clock here is 18 megahertz. So it's all happy. If we have a different clock in the EMU module than we do in our game module, it's not going to be happy and it's not going to write properly. And it took me some people on Discord to really help me out with understanding that. So we've got that for the character ROM. We've got the same for the PROM, but the only difference is we've got a particular chip select to know what we're downloading. And then we've got the same for each individual ROM file, so ROM A1, B1, C1, and D1. Now, what we need to do, a bit similar to how we decide data going into the CPU, we need to have a selection based on the address. And so we do that based on which bits are which. So the 13 down to 11 bits, if they're all 0, then it's going to be the first bank of ROM data. So that's the first 2K. After that, it's going to be a 1 for 13 down to 1, and the other bits are going to be 0. So we check for that, and that is the one that goes into RAM B1. Same for C1, except it's a 1 in that second position, and so on and so on. So this is how we define which bit of ROM data is being loaded from the MRA file into the ROM file. It's pretty neat. So basically, as I said, it's just a big bank of data that's taken from the MRA file, and it's fed as it reads it into whatever you're referencing, in this case our ROM files. And that's effectively what the MRA file is doing. So really good way of getting that done. So as I said, we've got our dip switch there settings, which is all being fed into our status bits that we looked at. We then have got our controls. So if we go down to here, our dip switch settings here, the controls are only used in terms of defining the controls, so we don't ever reference those again. What we do reference is the individual joystick settings. So each bit of this joystick is what you expect for up, down, left, right, and then the different buttons that you've selected. So the first buttons are always the same, and then comes whatever we defined in our on-screen display menu, and that's what we defined. And so it goes from bit 4, 5, 6, 7, 8, and then the test toggle is status 8, not joystick, because I'm taking that from a dip switch. And then we've got our dip switch here, which is status 8 again, status 9, 11, 10, status 13, 2, and 14. So actually we didn't need test toggle because we're just putting it there. What this allows us to do in the game, as we'll see, is in the on-screen menu we can put it into test mode, and we can change various things. We can move some of the bullets around and check if the RAM and ROM are good. The final thing to talk about is really probably one of the hardest things, is what this arcade video thing is doing. And this is where it gets to be a bit opaque for me, because we can actually look at the arcade video module, but it's effectively piecing it back together. So we're providing it the raw components like H blank, V blank, sinks, and then the individual pixels for red, green, and blue, and a clock, and it's taking all that in and it's piecing it together. It's giving you a CRT display, but it's also then allowing that to be put onto VGA displays or HDMI or whatever. Now, my main problem with that is this little bit here, which basically these bits are all being defined. So it says clock video is clock vid of this module, and all of these defined. This little thing is a catch-all that says anything I haven't defined, we'll just pick the variables that are already set here and put it into the module. And that's incredibly confusing as code, because these are all linked to the top module and all the other modules within MiSTer. And following this through is a real problem. So I've not had the best of luck with getting this all to work in different top modules, like taking different cores and porting my core into it. I've managed to find this one that works, and I can't necessarily do it with other cores with different clocks and different functions. But it's a work in progress. This one works for now, but I encourage everyone to be on their own journey to understand this arcade video module. It gets more complicated by the fact that two things I have not implemented on this core, which are implemented in a lot of cores, is one, high scores. So cores these days allow you to take a high score, to remember your highest score, and it loads it back in. And to do that, we have a separate high score module, which is referenced in this area, but we need to pass it a high score from the game. So that's gone for simplicity. Another one is a pause module, and pause allows us to pause the game either if the on-screen menu appears or if we just want to pause the game. Now that adds an extra complexity, because this arcade module then doesn't go game arcade module video out to HDMI. It goes game arcade module pause module, and it does something else that's even more opaque that I can't work out. So right now I can't get a pause module to work because it's doing something with the arcade video I don't get. So again, as I said at the beginning of the video, a bit more explanation is needed, at least for me, but probably a lot of other people, in terms of what this is all doing. I think this is the crux of it. All the other stuff is quite simple. This stuff is a little bit getting these modules to gel together. A lot of the guys have totally got it by the looks of it, because they get it to work great, but I've messed with it quite a lot and it's difficult. But it's a work in progress and we're getting there. Alright, so we are defining the buttons. Right, left, down, up, shoot, player 1 start, player 2 start, coin, and service button. And then what we're going to do is we're going to put the test mode on. So that resets the system. And then you can see we can move around the individual bullets. Then when we press the test button, moves to the next bullet. Not really sure what the point in this is too much, but it shows the system's working. And if we go back into the menu, we can change the number of lives. That changes the number of tanks there. Bonuses, 20,000 down to 10. There you go, 10,000 bonus. And then the coins. So that's obviously changing the dip switch settings, which is changing it in the core. Just like you'd be changing dip switch settings on the actual board. Set that back to 3. We want to play this game now, so put the test mode off. It resets. We're in the game. Put a coin in. There you go. It's 2 credits per coin if we put it. So now we're playing level 1. So the point is we're trying to shoot the tanks, the enemy blue tanks. So as we said before, one thing is that the bullets are white. In MAME they're blue. And the enemy bullets go straight through the walls in the MAME version, which they can't do. Not through the walls, but through the green borders, which they can't do in the hardware, so I'm not quite sure how that works. You see, I'm not very good at this game. Keep getting shot. But anyway, the game's quite good because the walls can be shot away and then it changes the maze. So what the enemy's trying to do is either shoot you, the yellow tank, or shoot the yellow eagle down at the bottom. And if they shoot away those walls and then shoot that yellow eagle, they win. And it gets rid of all your lives, so you lose the whole game. So if they shoot your tank, you just lost there. Going to start again. If they shoot your tank, you get 3 tanks to win the game. But if they shoot your flag, then that's it, end the game. So it's quite an interesting game because you can shoot away the walls and change the dynamic a little bit. And actually in level 3, there aren't any walls. So that makes it really difficult. And you are a little bit quicker as the tank than the enemy tanks. But you do have to hit them exactly on... You can see in this area here, I'm forced to be pretty much in line with the tanks. If I'm out of line with the tanks and I shoot them, they're not going to explode. And that's a slight frustration about this game. It makes it, especially when the walls are blown away, it makes it a bit tricky. Now that guy's going to come in and... Yeah, he shot me there, you see. So we've got a tank indicator in the bottom right there. We've got 6 tanks left to get. Now we've got 5. And then you can hunt after them. There is actually a cheat mode. If you put it in free play, you can then press the fire button on the menu and it takes you to whatever level you want to play. So that's good. So just 2 tanks left to get. Then I go chasing this guy. And he shot my flag, so that's the end of the game. I shot him at the same time, but not quick enough. So that's it. Good little game. It's very basic, but you know, it's 1980. What do you expect? But fun for a little while anyway. But it was really great to learn how to program it. So what have we got left to do? So the game works completely now. We've got the dip switch settings, loads from an MRA file, so that's good. So I've put it on the GitHub for release. Now you can tell there's no sound, and we do want to implement a bit of sound in this game. So I think what I might do is, first off, it's an analog sound system on the board, and that's not going to be the easiest to emulate in FPGA. So I'm looking at that, and I've discussed that with a few of the guys over on the Discord, what we can do there. But I think to start off with, I'll probably use a sample for the explosion sound, in the very least. In the game, actually, there is a slightly annoying tank sound that's pretty permanently on. So I don't think I'll implement that in terms of the sample straight away. Probably just implement the explosion sound, because that's a bit more interesting. And then after I've done that, if all goes well, then I can look at the sound circuit, the analog sound circuit, on a breadboard, maybe sample that, and then try and mimic that in the FPGA. Can't promise I'll get anywhere with that, but it's certainly worth trying. I think it'd be quite fun to get into audio aspects of this as well. So that's what is going to come up next in the next few episodes.